Hi, my name is Brendon Wright, and I'm going to be presenting the results of my project, which was a comprehensive investigation into the stability of Varian and Elector KV and NV imaging systems during ARC delivery, with thanks to Sir Charles Gardner Hospital and Genesis Care, and my supervisors were Pejman, Raushan Fazad, Ghulam Mubashir Hassan, Godfrey McWada, and Martin Ebert. So the first thing to talk about is image-guided radiotherapy. So image-guided radiotherapy is a specialized form of external beam radiotherapy, which allows for the reduction in margins around a tumor volume, as well as improvements in life quality and length. So if we look at the diagram here on the bottom left, the dose to the organs at risk and nearby to any tumor, if we use image-guided radiotherapy, are reduced, as well as a reduction in margins around the tumor itself. So image-guided radiotherapy uses images prior to or during treatment, such as CT images, MRI images, planar X-ray images. CyberKnife and Novartis both use orthogonal KV imaging systems. And these images allow for the realignment of patients, tracking of tumours, and managing of internal organ motion. So what do we mean by that in particular? So there are two margins that we need to be worried about when we're considering a patient treatment volume. So we need to consider the internal margin and the setup margin. So if we can track the tumor motion, we can reduce the internal margin due to intrafractional motion, as can be seen here. Whereas if we can reduce the patient setup inaccuracy, i.e. the interfraction movement, we can reduce the setup margin associated with tumors. Another important concept with regards to this project was that of the ISO center, of which there are three main types: the mechanical, the radiation, and the imaging. Ideally, we want an alignment of all three ISO centers. However, this is not always the case, as the ISO center tends to move around with gravity, mechanical irregularities of the machines, as well as wear over time. Down here are the guidelines for isocentricity as of TG142. So what is meant by the ISO center is, so for the mechanical ISO center, is the alignment between the axes of rotation of the gantry, of the collimator, and of the couch itself. And there are a few different ways to determine the ISO center. There's the mechanical pointer, the Winston-Lutz phantom, and other image-based verification methods. So the mechanical pointer is a device which is attached to the gantry head, and then there is a measurement of distance between the tip of the device and an object which is located in free space. However, this method is somewhat inaccurate, and it lacks reproducibility, as it's very dependent on the person who is measuring the distance, as well as the mechanical pointer itself being easily damaged. The next method is the Winston-Lutz phantom. So a ball bearing or another object is aligned to the room lasers for the particular linear accelerator, and radiographic film is placed perpendicular to the path. However, this has tended to become an imaging panel during as advancements in imaging have progressed. And then exposure is taken at cardinal angles, and a difference is measured between the center of the shadow of the sphere and the center of the field. And this is commonly used for quality assurance. Other image-based verification methods use phantoms to determine the isocenter movement. Different phantoms exist for different manufacturers, and they typically use digital images over film, as it saves in time, money, and also allows for the manipulation and storage of images for future reference, and quite commonly is used as routine QA. Another important image-based verification method that's used in research is that of the Hopf transform. The Hopf transform is a voting-based algorithm in which you create a parameter space and an accumulator array. So this is the accumulator array here, with our parameter space being in angles and distance away from our center point. For determination of where lines are in an image, you use the equation of the line and you iterate through the parameters for the equation of the line, adding votes when you find an equation which matches the points in your input image, and then you search for local maxima inside of your accumulator array to get your detected lines. This is the same process that is used for the determination of where circles are in an input image, but instead of using the equation of a line, and the equation of a circle is used. This method can be improved by restricting the parameter space used, but there is a trade-off between the parameter space and also the computational expense. If you have a larger parameter space, or smaller jumps in your parameter space, in your accumulator array rather, you have a more computationally expensive program. Another method which is used, which is one of the focuses of this project, is optical flow. Optical flow is an image processing algorithm which is used to analyze the movement in image between concurrent images. So the movement is described by the equation as can be seen here. If we assume that the movement is small and we take a Fourier series of it, this can be reduced to the equation as seen here. However, one of the issues with this equation is that there's too many unknowns with it. We have a movement in the x direction and a movement in the y direction, which we both can't account for. This is known as the aperture problem and can be seen by this diagram here. The barbershop pole example is a really useful one, as it seems like the image is moving upwards, where in reality the actual pole itself is rotating. So to solve this problem, we consider a region nearby to the actual pixel which we're trying to find the movement at. So one particular method, which is the Feinerbach method, which was used for this project, considers a polynomial expansion of the signal at each individual pixel. In terms of previous existing literature that is done for KV and MV imaging systems in isocentricity, there are only two main literature reviews which have done any sorts of investigation into the accuracy of KV imaging systems, and both of these are limited to only looking at the cardinal angles of the imaging systems themselves. So the aims of this project was to determine an independent isocentral evaluation method which can quantify the mechanical stability of both the KV and MV imaging systems and could potentially be used as a quality assurance check. So the linear accelerators used for this project, there were two Varian linear accelerators used, a Trilogy and a TrueBeam, both located at Sir Charles Gardner Hospital, as well as an Elector Access, which was located at Genesis Wembley. All three machines have a variation in terms of their age as well. The optical flow and Hopf transform methods were compared by attaching the phantom, as can be seen here, to the KV source of the TrueBeam linear accelerator, and then taking an image with it at its source position and panel position locked, and then shifting the panel by 1 centimeter in the lateral direction, taking an image and repeating that 4 times to compare the pairs of images. Sample output images are shown here. One important topic to be aware of is the notion of a covered source versus an uncovered source. For the TrueBeam linear accelerator, there is a cover that is on the outside of the KV source, as can be seen here, this grey cover. However, it was noticed during the process of attaching the KV phantom onto this source that it was prone to being moved around in both the in-plane and cross-plane directions. As a result, data was taken with the source covered, as can be seen here, and the source uncovered, as can be seen on the left here. The Winston-Lutz phantom was aligned to the room lasers and is a ball bearing attached to the end of a wooden rod which is extended out from the treatment couch. The image taking process was as follows. A sample image was taken at gantry 0 to ensure that the alignment of both the KV and MV phantoms were in the correct place. Once this was confirmed, the linear accelerator was rotated to 180 degrees, and then an image was taken every 10 degrees through to negative 180 degrees for both of the Varian linear accelerators, as well as additional images at gantry 0, whereas for the Elector, there are images taken using cine mode acquisition with approximately 360 images per rotation. With regards to the results, the first thing to note was the comparison of the Hopf transform and optical flow. So comparison was done in terms of accuracy and precision, and it was found that the optical flow displayed a higher degree of accuracy, whereas the Hopf transform displayed a higher degree of precision. The data for the optical flow was right on the limits of the accuracy of optical flow, which is purported to be about 0.1 of a pixel in terms of size, in this case roughly 40 microns. It was determined that we would progress with optical flow as opposed to Hopf transform, as we were rating accuracy as being more important for isocentricity as opposed to precision, as the average ever encountered for optical flow was only on the order of 10 microns, which in this sense is rather insignificant. It's worth noting that we have 8 different movement directions in which mechanical stability that we can encounter. So we can have our source sagging both in the in-plane direction and then in the cross-plane direction. We can have a sag in the source to detector distance. Our panel can sag in both the cross-plane and in-plane directions. Then we can have our panel turning, so a rotation around, and our panel tilting in both the in-plane and cross-plane directions as well. So the first data set that we'll look at is the Elector Linic in the KV plane. So an analysis was done between both a clockwise and counterclockwise rotation for the panel sag in the cross-plane direction. It was found that there was quite a varied difference between the clockwise and counterclockwise rotations, with only a maximum movement of about 0.6 of a millimeter encountered. In the in-plane direction, this was noted to be roughly the same, a little bit less in terms of the overall movement, only of the order of about 0.55 millimeters, but once again, a discontinuity between a clockwise and counterclockwise rotation. The panel tilt in the cross-plane direction was found to be quite similar for both clockwise and counterclockwise rotation, with a fairly consistent overlap between the data. It's worth noting that the overall rotation encountered is less than 0.1 of a degree. Same for the KV panel tilt in both the cross-plane and in-plane direction, where there is a quite clear sinusoidal trend and good overlap between clockwise and counterclockwise rotations. And also for the panel turn, where there was quite a prominent drop-off after 90 degrees and negative 90 degrees for the data. And this can be explained by the extension system which is used for the Elekta panel. The KV DD Sag was quite consistent between the clockwise and the counterclockwise rotation. It's worth noting that the error bars associated with this data are smaller than the figures used themselves, and as such are very hard to see. And the overall SDD sag encounter for the entire rotation was just over 0.1 of a millimeter. The source sag in the crossplane and the in-plane direction were the most interesting results as a result of this data. It's worth noting that the source sag in the crossplane direction was of the order of 5.5 millimeters, with a noticeable phase shift in the data between clockwise and counterclockwise rotations, and the source sag in the in-plane direction was of the order of about 4.5 millimeters, with a somewhat difference around the extremities for the clockwise and counterclockwise rotations. So to summarize the results from the Elector linear accelerator in the KV plane, there was a difference noted between rotation directions. The KV panel sag can be attributed to the extension system of both the source and the canal itself. The tilt and turn measured for the Elector were relatively insignificant, and the SDD and source sag can mainly be explained due to the pull on the gantry head due to gravity. Next, MBA comparison was done between the Trilogy, TrueBeam, and the Elector linear accelerators. So for the panel sag in the crossplane direction, it's worth noting that the Trilogy was the least accurate of the three, with the TrueBeam the most accurate. There is a trend for all three data sets, however, the trend is not the same for all three, and that the overall movement encounter was only of the order of about 2.2 millimeters at worst. For the panel sag in the in-plane direction, once again this is the same case. The TrueBeam is the most accurate of the three, and the Elector was the least accurate of the three. However, there's a less of a trend that can be displayed across all three data sets, and once again it's worth noting that the overall movement encountered is relatively small. For the tilt and the crossplane, this is actually reversed. The TrueBeam was the worst performing, and the Trilogy was the best performing. And a potential explanation for this was the additional weight that was added onto the panel itself to aid in portal dosimetry calculations. This is the same for the tilt in the in-plane direction, which again the TrueBeam was the worst, but however this case the Elector was the best performing. But once again this amount of tilt was fairly insignificant, but when compared to the tilt encountered for the KV system is quite significant. For the panel turn, there is a quite noticeable discontinuity in the data at around about 130 degrees as well as at gantry 0. However, this is explainable as during the course of the image taking process, we took images from 180 through to negative 110. Then it was found that the image at gantry 0 was missing, so we went back to the image at gantry 0 and then continued on with the remaining data points. And this could be a potential explanation as to why this occurred. Overall, the amount of turn was quite similar for the TrueBeam and the Trilogy, with the Elector being fairly accurate compared to the other two. For the SDD sag, the TrueBeam and the Trilogy were relatively similar in terms of performance. However, the Elector was the worst performing, displaying an SDD sag of over 0.3 of a millimeter. The gantry sag in the crossplane and in the in-plane direction were relatively consistent with previous literature into gantry sag, with the Trilogy, TrueBeam, and Elector all displaying patterns which have been previously tested before, and an overall gantry sag for both the TrueBeam and the Elector being of the order of about 0.1 of a millimeter, whereas for the Elector being, for the Trilogy being of the order of about 0.4 in the crossplane direction, and over 1.2 millimeters in the in-plane direction, thus exceeding the tolerance on isocentricity, as stated in TG142. To summarize the results of this data set, the panel sag was somewhat random for both the TrueBeam and the Elector, whereas for the Trilogy it kind of had a pattern for the crossplane direction. However, the data was within the limits for optical flow method. The tilt and turn was significant when compared to the KV imaging system, however, relatively insignificant when considering how much movement was occurring, being less than half of a degree in total. The SDD sag for the Elector was noticeably worse when compared to the Trilogy and the TrueBeam, whereas the gantry sag was the worst for the Trilogy and was outside of the tolerance set in TG142 in the in-plane direction. However, the data is consistent with previous research into gantry sag. The next data set that was considered was a KV in the TrueBeam and the Trilogy. This was to compare two different machines from the same manufacturer in terms of their results. So for the panel sag in the cross-plane direction, it's worth noting that the trilogy was considerably worse compared to the true beam data. It's also worth noting that there is an additional data set here, which is the covered true beam data. So as previously mentioned before, there was an analysis done between the covered and uncovered sources for the true beam, and this had an effect on the results that can be seen later on in this data set significantly. For the panel sag in the in-plane direction, the data was essentially random with a random outlier up the top here for the trilogy. The overall movements encountered for the panel sag in the in-plane direction were relatively small, however. For the panel tilt in the cross-plane, once again, the data is essentially random with a massive spread in the data points with relatively small movements encountered. And this is the same as what was seen in the tilt in the in-plane direction. There is a somewhat sinusoidal trend that can be seen. However, this is within the limits of the optical flow system, and thus it's hard to be able to attribute this to actual movement or whether it's just random noise which is causing this. For the panel turn, there is more noticeable sinusoidal trend that can be seen in the data here, with a very different sort of pattern seen for the trilogy and for the true beam. It's also worth noting that the uncovered source for the true beam displays a completely different pattern when compared to the covered source for the true beam. For the SDD sag, this again is repeated with the covered source displaying a larger SDD sag when compared to the uncovered source, and the trilogy and true beam having comparable sinusoidal shapes, but in terms of 180 degrees shifted from one another. For the source sag in the cross-plane direction, there is a noticeable difference again between the clockwise and between the uncovered and covered sources, as well as between the trilogy and the true beam, with the source sag for the trilogy being considerably worse compared to that of the true beam. And this is also repeated in more dramatic fashion in the source sag in the in-plane direction, where the trilogy had a source sag of up to nearly 4 millimeters of movement, whereas the true beam encountered a source sag of within 1 millimeter of movement. And once again, it's noticeable that there's a significant difference between the covered and uncovered sources. To summarize the results, there was significant difference between uncovering the source, noticeably for the source sag, which would be expected as the source sag would be causing, the cover itself would be causing source sag movement. Significant panel sag for the trilogy in the cross-plane direction. The tilt was essentially random for all the machines. However, there was a somewhat clear trend. Despite this, the tilt was roughly insignificant. Same with the turn. The SDD sag had a somewhat discernible trend. However, the movements were small, and there's lots of noise in the images out of the trilogy, and therefore it's hard to be able to determine whether this is the result of noise or whether this is actually SDD sag occurring. And there are large amounts of source sag, particularly for the trilogy. The last data set to consider was the KV true beam comparing a clockwise and counterclockwise rotation. So as mentioned before, the KV panel sag has a somewhat discernible trend. However, there is a fairly consistent overlap between clockwise and counterclockwise rotations, and similarly to the in-plane direction, there's a lot of overlap. The overall movements for the cross-plane and in-plane panel sag were less than of the order of 0.1 of a millimeter, so relatively insignificant. For the panel tilt in the cross-plane and in the in-plane direction, the amount of tilt uncovered was less than 0.5 of a degree for both directions, with there being a more clear trend in the in-plane direction and not a discernible difference between a clockwise and counterclockwise rotation. For the panel turn, there is once again a clear sinusoidal trend here, with a slight difference between a clockwise and counterclockwise direction, but overall movement for the panel turn was just over the 0.1 of a degree. The SDD sag once again also displays this sinusoidal trend with a slight difference between clockwise and counterclockwise rotations, but overall the SDD sag was of the order of 0.01 of a millimeter and thus relatively small. For the source sag in the cross-plane direction, there was a noticeable difference between a clockwise and counterclockwise rotation. There is a significant agreement for the counterclockwise rotation data points, with them almost overlapping for the entirety of the rotation, and quite a pronounceable difference in the clockwise direction. Once again, this pattern also appears in the source sag in the in-plane direction, with a noticeable discontinuity at around about gantry 0, suggesting that there is a mechanical instability at gantry 0 causing this noticeable difference between the source sag in the clockwise and counterclockwise directions. To summarize the results, the panel sag has a clear trend with a difference in rotation probably attributed to just noise. Tilt also had a clear trend but was different mainly just due to noise. Turn had a clear sinusoidal trend, but there was a noticeable difference in rotation direction which was causing this. SDD had a clear sinusoidal trend, but there was no discernible difference in rotation. The The source sag had a clear difference in rotation direction, which was attributing to the difference between clockwise and counterclockwise rotations, and the majority of differences in rotation direction can be mainly attributed to the movement of the source itself. An RMSD calculation was done comparing the clockwise and counterclockwise rotations for the true beam in the Elector data in order to compare the consistency in clockwise and counterclockwise rotations. It was found that the source sag in the crossplane and in-plane direction was the most varied data in terms of agreement between clockwise and counterclockwise rotations. And for the Elector, there was a noticeable difference in panel sag in the clockwise and counterclockwise rotations for the crossplane and in-plane directions. In terms of the maximum movements encountered in the MV direction, it's worth noting that the source sag in the in-plane direction for the trilogy exceeded the guidelines set out in TG142, as well as the trilogy having an extreme amount of movement for panel sag in the crossplane and in-plane directions. However, the true beam was the worst performing in terms of tilt in the crossplane and in-plane direction, mainly due to the additional weight which was put into the panel to aid in epidensymmetry. It's also worth explaining that the true beam is able to deliver only up to 9 MV beam, whereas the trilogy can deliver up to an 18 MV beam, and thus there are extra shielding requirements for the gantry head for the trilogy, which is likely to explain these additional source movements when compared to the Elector and the true beam. The maximum movements encountered in the source plane were all relatively significant for the source sag in both the in-plane and cross-plane direction, with very few movements being less than the 1 millimeter tolerance. The panel sag in the crossplane and in-plane direction was particularly noticeable for the trilogy, as well as for the Elector in both clockwise and counterclockwise rotations. In terms of future work that can be done with regards to this project, the movement of the source of up to 5 millimeters for the Elector can lead to an image deformation during CT reconstruction, particularly noticeable in terms of a ring artifact when doing the reconstruction, and thus being able to track the source movement and being able to apply a correcting factor to predict this movement can lead to the reduction in this ring artifact occurring. The improvements in KV-CBCT can lead to the implementation of adaptive therapy inside of radiation treatment and can allow for better treatment outcomes for patients. And the ability to find a new novel method in optical flow as opposed to half transform can allow for the assistance in real-time tumour tracking, as the method itself tracks based off of intensity gradients rather than based off objects, and therefore it can track just based on the tumour itself rather than having to insert fiducial markers. So in conclusion, I was able to develop a novel phantom which provided an independent check in terms of mechanical stability, with optical flow being a more accurate method when compared to the half transform. Additional information about mechanical stability in terms of not just imaging at cardinal angles, but in terms of during full gantry rotation, allows for an in-depth prognosis as to the performance of machines, with the most accurate machine being able to be used, well, recommended to be used for any sort of stereotactic treatments. Potential improvements for KV-CBCT image quality in terms of tracking the source movement could be used, and the age impact is consistent with the literature that was found. So with the worst performing machines being the older machines themselves, and this is the most comprehensive investigation into any KV imaging system ever undertaken, with the data being able to track 8 different parameters during full gantry rotations. These are the references from the literature and my acknowledgements. So once again, thank you to Sir Charles Gardner Hospital and to Genesis Care for letting me take data on their linear accelerators, as well as to all of my supervisors and everyone who's assisted me during the course of this project. Thank you very much. Does anyone have any questions?
You talk about the limits of the optical flow algorithm.
Yes.
So what are some of the factors that impact that? And after having done all your results, is the limit sufficient for the measurements you've done?
So one of the reported limits for the accuracy of optical flow is about 0.1 of a pixel, but it's also dependent on a lot of other factors in terms of, if I go back to, it might be better just to go escape out and then scroll up here.